In this talk, I will present CutNetVis, a new method for visualization of semantic relationships in high-dimensional categorical data. I want to start my talk using an example dataset that evolves around different mushrooms. The toadstool is a poisonous mushroom that probably everyone knows due to its characteristic appearance. But how can I tell if a mushroom is edible or poisonous? Different dimensions can describe the mushroom, which might be useful to tell apart poisonous from edible mushrooms. Such dimensions include the cup shape, the surface or the color of the mushroom, the odor of the mushroom, different attributes about the gill and its spore print, information about the stalk, and many more attributes, such as the wheel type and wheel color, the ring number or the ring type, if the mushroom has bruises, its population, or its habitat. In the end, we can connect this information to a class variable, which is also a categorical dimension and tells us if the mushroom is edible or not. Now, we want to come back to our original question. Altogether, our dataset holds 23 categorical dimensions. These dimensions each have a set of values which we call categories. We're interested in the frequency and the relationship between those categories. And what are possible approaches to visualize this information? Mosaic plots can be used to show the relationship between two categorical dimensions and show the frequencies of the co-occurrences. In this example, we see that the edible mushrooms more often have bruises than no bruises. For the poisonous mushrooms, we can see that the opposite is the case. The mosaic plot can give us a quick overview of the relationship between two dimensions. The main problem with mosaic plots is that they are limited for two dimensions. Although some approaches for multivariate contingency tables exist, these become difficult to read. Another approach in order to visualize the relationship between the categorical dimensions is the parallel sets plot, short PSP. The PSP splits the data set vertically along the categories for a certain dimension. Horizontally, the data set is split in every axis, which are representing the dimensions. From this display, one can draw conclusions about the relationship between the categories. For example, we can observe that the edible mushrooms have often no odor. From these odorless mushrooms, the ones that appear in the solitary population, most of them appear in the woods. A problem with the PSP is that it becomes cluttered as the number of dimensions or categories rise. The multiple correspondence analysis, or MCA, uses dimension reduction in order to project the categorical data into the two-dimensional plane. It works by translating the categorical data into binary numerical data by using a BERT table. In our example, we colored the various categories by the majority class in that category. This method has similar drawbacks as the PCA, which is used for numerical data, such as distortion effects and sensitivity to outliers. Our motivation is to overcome issues with current methods, such as mosaic plots are only suitable for a small number of dimensions. PSP have a similar problem and become cluttered because of the crossings of the lines. Also, they require ordering, which is non-trivial. Dimension reduction, such as MCA, removes interpretability and introduces distortions and is sensitive to outliers. Also, MCA often leads to overlapping labels when there are many dimensions. Our idea is to use a network in order to visualize the semantic relationship between the categories. Next, I want to explain our concept and how our information is encoded visually. The position is calculated iteratively using the force-directed graph layout. Nodes which have connections get attracted, and nodes without connections get repelled. The forces that attract and repel the nodes are updated in each step. The position of the nodes is merely a result of that and does not result from either MCA, MDS, or any other projection method. The color of a certain node is given by the color code of the majority class, the class with the most entries. The size of the nodes is proportional to the number of elements that belong to the category. The label shows the category with its corresponding dimension. The higher the entropy of the node, the higher the font size of the label. The line width of the edge is proportional to the association between the source and the target node. The edge line length. The edge line length is a result of the force layout and does not encode any information itself. In this example, we can see the whole 23-dimensional mushroom dataset. First, we can observe a fully connected graph with lots of edges and circles that overlap. By filtering the edges by the weights, we can declutter the graph and see that connected communities appear. We then can look at these communities in detail. When we hover over a node, we can see the class distribution and its entropy. For example, we can see that the GIL color orange is connected to the attribute wheel color brown, which is mostly associated with edible mushrooms. These categories are connected to the habitat leaves, which is mostly an attribute of poisonous mushrooms. The habitat leaves is also connected to the cap color brown, which is again an attribute of mostly edible mushrooms. These statements about the semantic relationships between categories can lead to insights about which attributes make a mushroom edible or poisonous. In this example, we see a different use case using the life expectancy dataset. The dataset has demographic information about different countries and their life expectancy. We used quartile binning to categorize the life expectancy and other numerical dimensions into 3 categories: low, medium, and high. In this example, we can see that in the class that has low life expectancy, categories like low schooling, high mortality, and high prevalence of HIV are correlating. In the class that has a high life expectancy at birth, we can see that when schooling is high, also the ICOR is high, which is a measure of how good a country is utilizing its resources. Also, we can see that these countries are mostly developed countries. For the analyst, it is interesting to see where countries are placed in the global relationship of those categories. With this example, we showed that our approach also works for numerical values and for more than 2 classes. Now I want to discuss the advantages and limitations of our method. The advantages are the following. The case studies showed that semantically connected communities appear, which might be interesting to investigate for the analyst. Compared to the other approaches, our method is also suitable for a higher number of dimensions due to the force-directed layout and filtering options. Avoiding the problem of overlapping labels and distortion effects as it appears in the MCA plot. Limitations are: communities sometimes disappear from the layout because of the repelling forces. On top of that, edges can introduce clutter, but the option for filtering and hiding the edges is given. Furthermore, applications of the method should be studied by the user studies. For our future work, we have several ideas. In order to profit from the advantage of the different approaches, we want to use linked views to link CutNetWiz with, for example, MosaicPlot, PSP, or MCA. The linking could be achieved by the use of brushing or selection. Edge bundling is a method that reduces clutter, which is especially helpful in larger networks. To evaluate CutNetWiz empirically, We want to create a user study. The user study could be in form of a task-based evaluation. Such tasks might include finding the most strong correlation between categories of more or two dimensions, detect certain groups of categories in the network and compare finding them in the MCA plot, or answer a specific question about the dataset.